With a two-sample hypothesis test, when we have independent samples and the population standard deviation is known, we can make some inference about the information. Let's have a look at the example. You are trying to determine whether students perform better in an in-person class or an online class. You anticipate that students perform better in an in-person class. Now, you have no statistical evidence. You are saying this because this might just be based on your experience or just your beliefs, but we can test it. You take a sample of 16 students from each class. The sample from in-class got an average mark of 80%, and the sample from from the online class got a mark of 75. The population standard deviation for in-class is 9, and the population standard deviation for online is 14. You want 95% confidence. So the first thing that I would do here is just organize the information. So we have in-person classes, online classes. The sample mean of marks for in-person is 80, and the sample mean of online courses is 75. The standard deviation from the population, not from this sample, in-person is 9, and the population standard deviation for online is 14. And the sample size is 16 for both. Now we can set our hypothesis. Now our null hypothesis is what we anticipate. So our anticipation is that students perform better in an in-person class. So what we want to know is the mean of in-person class, which we'll call 1, less than the mean of online class, which we can delineate as 2. We're saying that you will perform better, so this will be a positive number, more than 0, right? Because a higher mean of our in-person would mean that after we less our online, we would have more than 0, a higher mean. Our alternative hypothesis will be the opposite. Less than or equal to, because this would mean that it's more than 0. So if there's no difference, we would have a difference of 0. It would be less than or equal to 0. So, in plain English, our hypothesis is that in-person classes, students perform better than online classes, shown here. We now need to use our equation, which we can do for the two-sample hypothesis test. And we can get this from our formula sheet. So we're trying to determine our probability. To determine our probability, we need the z-score. So z equals the population the population 1 mean less the population 2 mean, in-person versus online, less the sample mean less the sample mean minus the population mean for in-person minus the population mean for online, which we don't know. the standard deviation squared for sample 1 divided by the sample size for 1 plus the standard deviation squared 2 divided by the sample size, and all of this will be, we will take the square root. So we can now start to fill this out. Our sample average here is 80 less 75 less 0. We don't have a population mean. Our standard deviation for first is nine squared over 16 plus 14 squared over 16. So we have 5 oops. In the next step, +81 plus 196 is 277 divided by 16. The square root is 4.1608. Five divided by 4.1068 brings us to 1.20. So we now have a z-score of 1.20. When we have a look at our probability table, we see that 1.20 brings us a probability of 88.49%. A probability of 88.49%. So let's review our hypothesis. Based on our two independent samples, we wanted to see if we could, if this hypothesis could be rejected. We had a 95% confidence level, so that means that unless this sample was so rare that we would only see it 1 in under 5%, then we could reject it. Well, this is 88.49%. So although we can never say that our null hypothesis is true, we can say with a fair amount of certainty that it is very likely to be true. At 88.49% of the likelihood of seeing a sample set like this, this would be something that is very likely to be true. So we don't reject our null hypothesis. We will reject our alternative hypothesis, and we can conclude that it is likely true that in-class learning is better than online learning.